or the front, and then the rear does not delete in the queue. And as usual, as we saw in the other data structure, we have the is full and then the is empty. So the is full validates if the queue is actually full. And then the is empty also checks if the queue is empty or it's not empty. And then we have another one, which is the size. So this operation returns the size of the queue, which happens to be the total number of elements that the queue actually contains. So if you want to issue the queue, you know for sure that the element in it are 20. So use 20 as a hard code value to check for the availability of elements. So it's best to use the size of or the size to check the number of elements or items in the queue. So as we said earlier, the enqueue operation in the queue data structure basically adds an element to the end of the queue. And this is a simple pseudocode algorithm that shows how it works. Or if you're asked to write a simple pseudocode that will enqueue an element in a given queue, this is the steps you're supposed to follow. So ideally, you have to check if the queue is full to avoid any queue overflow stuff. That's the first step. And then the second step is if the queue is full, then you have to return an error and then you exit. So if the queue is full, you need to prompt the user that the queue is full and then you exit, so that the person will know why he was not able to add any element onto the queue. However, if the queue is not full, then you increment the rear pointer to point to the next empty space. We increment the rear pointer to point to the next empty space. That's the third step. And then the fourth step, we add the data element to the queue location where the rear is pointing. And then we finally return a success message that your queue, your element has been added or has been enqueued successfully. And then the code exits. So this is a simple pseudocode to enqueue an element in a queue. So basically, this is a diagram that shows what we just spoke about. Right, so the first is we have the first queue over here. So this is the first queue that we have. And now we are trying to enqueue with the element 5.
Sir,
over here.
the network is very, very bad. Very bad.
Right. So we said earlier in the algorithm that we need to Is it for only him or everybody? Henry?
Yes, sir. Please, the network is it's very bad. It's kind of breaking. Your voice keeps breaking.
We are experiencing it.
Yeah, so I'm saying that your network is very bad, and we are experiencing this breaks in your lecture. Hello, sir. I don't know if you can hear us.
All right, let me.
Okay.
But it's okay now.
Yeah, it's a bit better, but you kind of go off a little bit. It goes off a little bit. It kind of breaks.
Oh, okay. It's okay now. It's still the same problem.
So it's okay for now. In case it happens again, we will notify you. So
Hello?
it's okay for now, but in case it happens again, we will notify you, please.
Oh, use the yellow to circle around is the initial queue that we have, and we are asked to enqueue 5 into the queue. And then we need to take note of 2 pointers over here. So the first pointer will point to the rear, and then the second pointer will point to the front, right? And in the algorithm, we said earlier that if the queue is not full, then we have to increment the rear position to point to the next empty space. So obviously what we are trying to do now is to point this particular arrow here onto this next space, which is this one here. And then finally we insert or we enqueue the 5 in that particular empty space indexing. Now the position for 10, which was initially the first pointer, has now changed to 2. And the new element that was enqueue has now taken its position as 1. And now we have 0 here, which also means there's no value at the first position or the position 0. So this is the before the enqueuing, and this is the after enqueuing. All right, let's go to the dequeuing operation. And we said earlier that the dequeuing operation moves the first element from the queue. The queue removes the first element from the queue. And this is how the algorithm works. So we check if the element. However, with this one, we need to check and see if the queue is empty. If the queue is empty, we return the underflow error and exit. Hello? Valencia.
Hello, sir.
All right, so let's go through the algorithm. Hello, Valencia.
Yes, sir. The network again. All what you said, you were just breaking. We didn't hear anything.
All right, so let me go back again if you can hear me. All right, so what I was saying is that this is a diagram to show or indicates how the enqueuing really works, right? And the first one we have is, the first one we have here is a before the enqueuing process. And before the enqueuing, we have 10, 15, 20, 30, and then 40, right? And we just did the numbering at the top to show how the enqueuing will work after we've inserted the value. So we start 0, 1, 2, 3, up to 6. And 0 and 6 happens to point to, and now let me say now, and values, that there's no values in it. So actually what we are considering here is from 1 to 5. And from 1 to 5 have values in it. But as we said earlier, we need to take care of two pointers. The one which points to the rear, which is the end, and the other which points to the front, right? And we said in the algorithm that if the queue is not full, what we have to do is increase the rear pointer to point to the empty space. So this is the rear pointer. And for it to be able to point to the empty space, we have to move backwards one, or like this particular index 0 here. So instead of the pointer pointing to 10, in the enqueuing process, we shift the pointer to point to 0, the numbering at the top. And now when we are done, we now insert our value at where the pointer is pointing. And this point is going to be this place. Because earlier that was the empty space we had at the top here. So after shifting this to point to the empty space, now we fixed or we add the element into that empty space. And then that will be it. But then for us to be able to know how it really works, we now have to update the numbers we had over here. So earlier, the index 1 had 10, but then since we have now enqueued the value 5 or the element 5, now the element 5 takes the index 1 position, and then 10 will take 2 in that order until the end. So the only thing you have to notice is that you first check if the queue is empty. I mean, if the queue is full. If it is full, you now print an overflow error. If it is not full, you change the position or you increment the rear position to point to the next empty space. Now you add the value and then you return a success message for the user. So that is how the enqueuing really works. And the dequeuing removes the item or the element from the queue. And instead of checking for is full, we need to check for is empty. So if the queue is empty, then return underflow error and exit. If the queue is not empty,
Sir.
if the
Sir.
hello, can you hear me?
Yes, sir. Hello.
All right, talk to us.
Okay, so sir,
Yeah, we can hear you.
at what point in time do you say that? Yes. So at what point in time can you say that the queue it's empty? Is it because it's having empty spaces both at the rear and then at the front? And at what point in time also do you say the queue it's full? And when it's full, how is it going to be represented per the diagram you displayed? We know that the diagram shows the queue is empty and there's space because both at the rear and at the front there are spaces there. But when it's full, how is the diagram going to be like?
When it is full, then it means that we don't get empty spaces at both ends. So more like we are going to get something like this. So we are not going to get all of these ones are going to be removed. This one will be removed for us. So you're going to get actual cells with values in them up to from the beginning to the end. That is how the queue is going to be indicated as full. Right. But then since index 0 and index 6 doesn't have any values, that is why we are assuming that this queue is not full, and then we can insert items in it. But in actual programming concepts, we learned earlier that you either declare the queue with value in them to specify the item that you want to, number of items you want to store in the queue. So in that instance, if let's assume that you have a queue, maybe list of names, and you specify a value like 5, and you actually inserted 5 names in it, or you have enqueued 5 names already, ideally then the queue is full because you said the queue should contain only 5 names, and you've been able to enqueue the 5 names, so the queue is full in that instance. Please, are we? So in a diagram, if you want to know if the queue is full, then the edges, the far end and the beginning would have values filled in the cells. So all of these ones are going to be removed. All of these ones are going to be removed, leaving only 1 to 5 with the values 10, 15, 20, and then 40 in it. Then the queue is full. However, since we have empty spaces at both ends, then we could say that the queue is not full at that point. Please, I hope it's clear.
Yes,
So
it's
this
clear.
is also the queuing pseudocode. So we have step 1 up to step 6. All right. So we have step 1 up to step 6. So as usual, we check if the queue is empty, because we cannot remove any item from an empty list or whatever it is. So we have to check if it is empty. If it is empty, we have to return an underflow error, and then we exit from the code. If the queue is not empty, that is an element in it, then we have to access the data where the front is pointing. And then we increment the front pointer to point to the next available element. Then we return x-axis. Before at the top.
Hello. Sir, please, the algorithm for the enqueuing and then the algorithm for the dequeuing. Please go back to the enqueuing slides. I want to clarify something for myself.
Hello, Prince.
Hello, sir. Please, I said the algorithm for the enqueuing and then the algorithm for the dequeuing. I'm confused about it. Yes, please.
Yeah.
This slide. The first 2 steps. This one is enqueuing, and the enqueuing is to add an element, right?
Okay.
And we say we should check if the queue is full. So if it's full, we can't add. And then the other algorithm for the dequeuing. Dequeuing, we are to remove. So we check for emptiness. So if it is empty, we cannot remove anything.
Yeah.
All right. I'm fine. Thank you.
Exactly.
Yes, please. I'm okay.
Henry, is the network okay now?
Yes, sir, it's a bit stable.
Oh, okay.
I don't know. It's kind of you have a
So
delayed
this is
feedback. As
also
in,
the diagram
when
to
you
show
talk, it takes
how the the queuing. Oh, okay, okay. I think probably the next question transmission. It's so earlier we have our queue, which we have to the queue, and as usual, we learn that the queue removes the element from the front. So basically, we are trying to remove this particular element from the queue, right? And then we check whether it is the queue itself is empty. If it is not empty, then we proceed and change the pointer, which was pointing to this at index 5 to that of index 4. And in the process of changing,
Very bad network. Charlie. Baddest. The baddest.
Wallahi, Papa.
Yeah, man. The baddest.
Then, like from his end, because we can hear ourselves very well.
Sure.
Prince. Hi, you did 24/7.
Charlie, I mean, this time they have serious.
Please, I've asked the question on the page, so please let's answer me on the page so that we know what to do. Please, the data structures page. Thank you.
Henry, can you share the link? Because some of us, I think we are not on that page. Thank you.
Please, are you in the community already?
Oh, okay. Then that's fine. Okay, thank you.
All right, so let's continue, hoping that the network will be stable now. So now let's go through the queuing process to see how it also works. So earlier, this is what we have as the queue. This is the initial queue that we are supposed to queue a value from. And the queue, you don't specify the element you want to dequeue because we dequeue from the front. That is the default settings for queue data structure. So obviously we have from, let's ignore the 0 and the 6, we have 1, 2, 3, 4, 5. So obviously we are trying to now dequeue the element 40 from the queue. And all we have to do is just change the position or the pointer, which is pointing to the 40 to the next element, which is 30. And then that means that we have actually dequeued or removed the 40 from it, because ideally it is a pointer that points to the location of the element. However, if it is shifted to the next, it means the other one has been removed from the queue. And that is how it works. So the algorithm states that we check if the queue is empty. And then if the queue is empty, we have to return an underflow error and exit. However, if that is not the case and the queue is not empty, you have to access the data where the front is pointing. And then after that, we increment the front pointer to point to the next available element. And then we return a success to show that the item has been dequeued successfully. And after the dequeuing, this is the original or the new data structure or the queue we have, which is with element 10, 15, 20, and 30, whilst 40 has been removed from it. So that is how the enqueuing and dequeuing basically works. I hope the network is fine.
Yes, sir. It's fine.
Yes, sir. So in brief,
Okay.
In short, we dequeue from the rear. No, we enqueue from the rear and then we dequeue from the front. I don't know whether I'm right.
That is how it works. Yeah. That is how it works. So we enqueue from the rear and then we dequeue from the front. All right. So in the process of choosing which data structure is best for us, it is very important that we check for each of the basic operations on that particular data structure, their complexities analysis before we choose which one is best. And for the queue data structure, the basic operation has the following: time complexity analysis and space complexity analysis. And for the enqueue, the queue, the front, the back, that is empty and that is full, all of them have a big O notation of 1, which basically means that it's a constant time operation. And if you can remember from your algorithm classes, you know that whenever an operation has a big O of 1 notation, that is very much desired compared to the other notation like big O of n raised to the power 2, raised to the power 3, raised to the power 4, or big O log n, and all those stuff. So this basically means that if you have a program you want to write in computing system and much of the operations that you're going to be performing involve these 6, then it is best for you to use a queue data structure. So if much of your basic operations on the data or within the system is going to be enqueue, dequeue, bring out the front element, taking the rear element, checking for it's empty and then it's full, then you can go in for the queue data structure to implement your code or any logic you want to write. So all of these operations have big O notation of 1, which is a constant time operation. So probably in the exam, the objectives, we can give you an example like in the NQ basic operation. What is the time complexity? What is the space complexity? Now you should know that it is big O of one notation. So it's clear.
Yes,
All right,
sir.
so let's look at some applications of the Q data structure. Okay, so the queue is used when things don't have to be processed
Sir,
immediately, but have to be processed in first order. Dennis, Amosa Dennis.
thank you, sir. Looking up to the time complexity and the space, it seems like the big old one, they are all affecting the NQ, the DQ, like everything is the same. If I'm right.
Yes, that's how it's supposed to be. That is how it's supposed to be. Yeah, you're right.
Okay, but okay, let's take it that way. Okay. Thank you, sir.
So let's look at the application of the queue data structure. And if you have items that are not supposed to be processed immediately, but then have to process in first order operations or structure, then it is best to implement them in the queue data structure. That is, if this one comes in first, it's supposed to be processed before the other, then you can go in for the queue data structure. And then when a resource is shared among multiple consumers, so an example includes the CPU scheduling and then disk scheduling. I believe you learn operating system, so you know what CPU scheduling and disk scheduling basically is or are. And also one other application of the queue data structure is if you want to transfer data asynchronously, that is data not necessarily received at the same time or at the same rate in which they are sent between two processes. Such processes that are in that particular form, you can also go for the queue data structure. And examples include input operation, file input output, and many others, and mostly server as well, where you are consuming an external API because the responses are not actually asynchronous. That is, one will come in before the other. And it's best for you to use a queue data structure as well. And then for linear queue, a linear queue is a queue where data elements are at the end of the queue and from the front of the queue they are received. Then you go for all right. A first process before the other. And this example is mostly used in printers. So the instructions that is first given to the printer is the one that will be executed first before the other ones follow. So in a printer situation, for instance, linear queue is implemented. That is, if you give an instruction to print your, payroll for your, let me say your employees, and then after that you give another instruction to print maybe a memo, then the payroll for the employee you have to print it first because that came in first, and then followed by the memo for a meeting or whatever it is. So if you want to go in for such a process where the items are processed in order which they came, then you can go in for a linear queue to implement your code. And then also we have the circular queue, or we learn about the circular queue, which is quite similar to the linear queue, but the end of that particular circular queue is connected to the front as well. And then it allows for efficient use of space, memory, and can improve performance. So some of the applications are where the data element need to process in a circular fashion. So if your information needs to process in a circular fashion, or data need to process in a circular fashion, it is also important to use the queue data structure, but specifically the circular queue. And examples include the CPU scheduling and the memory management as well. And then we spoke about priority queue. So priority queue is a type of queue, as we learned earlier, where element is assigned a priority level. And those with the highest priority, in most cases, are processed before element with the lowest priority. So in some applications where certain task or data element need to be processed with higher priorities, then you can go in for the priority queue. And examples include the operating system task scheduling and network packet scheduling. So if you want some network packets to move before others, then you have to use the priority queue to give priority to those networks for others. And priority queues is implemented. You have to get access to all your computer system, or let me say the various peripherals connected to your system before. So if there's any error within the kernel, you cannot use the system. So there's priority given to the kernel operation over the user being able to operate the machine. So until the kernel is fully functional or is fully stable, let me say it that way, then the user cannot have access to the entire system. So that's a priority that's being given to the kernel over any other application within the operating system. And then also for double-ended queue, which is also known as a queue, and it's a type of queue where element can be added or removed from either end of the queue. And it allows for more flexibility in data processing, and in some applications, or some of the applications, is where elements process in multiple directions. So if you have your element that could be processed in multiple directions, then it is important to wait for the double-ended queue. And some examples include the job scheduling in CPUs and some search algorithms as well. Where you search in both directions to be able to find maybe if this is the shortest path, which is not appropriate. And then we got concurrent queue. So where concurrent queue is a type of queue that is designed to handle multiple accessing queues simultaneously. So thread would access the queue simultaneously. And then in the FSA manner. And examples include data transactions and web server request. So when you make any transaction, let me say on your banking application, there are so many simple applications that begin to run. So all of these ones will have to use the information that they provided, especially let me say your bank account within the system. So let me say, a thread will have to be initiated or executed to check and see if your balance is sufficient enough to make the withdrawal. And another thread will have to also be executed to check if the account username matches the person who is doing the withdrawal, and many other threads will be executed. And in this process, the data that you have in the bank will have to be accessed by all of these threads. So if the data is not stored in a double-ended queue, there's going to be what's the word? There's going to be deadlock, because one will be using the data and then the other will have to wait for it to finish before it uses it. However, if we use the concurrent queue, it means that all the threads that have been executed will now have access to the various data that we have. And that is, if you have a scenario like that, you can go in for the concurrent queue data structure as well. Now let's look at some issues that we can talk about in the queue data structure. I think we've heard of the first two for quite a long time. We spoke about the queue overflow, the queue underflow as well, and then we have priority inversion. So priority inversion occurs if in priority queues when a low priority task hold a resource that a high priority task needs. So assuming that you give an instruction which is not of, let me say, has a very low priority, and it is using a resource that a higher priority instruction needs. That is an example called a priority inversion. This can cause delays in processing and can impact system performance, because the one with the highest priority will have to wait for the low priority task to finish before it gets access to the resource. And that is going to delay the processing of data. And then we have the deadlock situation. So which occurs when multiple threads or processes are waiting for each other to release a resource, which is also the situation when multiple threads execute to check for account balance, and if the name matches the person who wants to withdraw, then it means that if one thread is using your information, it will have, the others will have to wait. When the other one finishes, then they uses those ones. That is what we call the deadlock over here. All right, let's look at some other issues as well. So one other issue is the performance issue, and which can be impacted by various factors such as the size of the queue, the frequency of access, and the type of operation performed on the queue. And then if there's any queue performance, especially those that are very poor, it can lead to slow system performance and reduce user experiences. Mind you, the one we showed you earlier, the enqueue, the queue is full, and the rest are just the basic operation that we can perform on the queue. But you might want to define some other operation that you want to perform on your queues, and that can lead to slow system performance, and then it will reduce the user experience as well. And the other issue is synchronization issue. So this can arise when multiple threads tend to access the same queue simultaneously, which can result in data corruption, race condition, and other errors as well. And then there's also another issue, which is memory management. Some of the queues can use up to a significant amount of memory, especially when processing large data sets. And some of these ones could be memory leaks and other memory management issues. Can lead to system crashes and several other errors that may arise. So these are the issues and applications of the data structure. Then you have to sit now and choose which of them the data structure is actually best for this particular client, or is it necessary to combine all the data structure or some of them to make the system more robust or efficient? Please, any question on the key data structure? Do you have questions on the queue data structure?
Hello, sir.
All right.
Hello.
Qubit, you have a question?
No, so I wanted to ask about this kind of slide. Like, what slide is this one? Like, is it lecture 4, lecture 5, or whatever? I can't see it from my end here.
Oh, okay. Let me confirm. I think it's supposed to be 4. Yeah.
Okay.
Yeah, it's 4. Yeah. All right, so trees, and I believe all of us know trees, right? At least one way or the other, we've sat under a tree before. It's a data structure that can be used to store information. And the previous data structures we learned about the examples of linear data structure. The stack, the queues, the linked lists, and the rest are examples of linear data structure. But then what we are trying to do now is, and I think this week or probably today, we can talk about graphs as well, are examples of non-linear data structure. So we just have an overview of how, different linear data structure is from the non-linear data structure. We talk about what a tree data structure is, some basic terminologies in tree data structure, some properties we can speak about, and then what tree is not, applications of trees, and ultimately we talk about basic operations of a tree. And also, I believe you're familiar with spanning trees from the algorithm class as well. So we talk about this today, and probably there's enough time you will just have an overview of graphs and we'll close. So we've seen this picture before, which is the broad data structure and its various subdivisions. So under data structure, we have the linear and then the non-linear. So we've dealt with all of the linear data structure, which is these ones over here. And what we are going to do now is to talk about the non-linear data structure. But then we are starting with trees for today. So just a brief comparison between the linear data structure and data structure. And I believe we've seen it before. Linear data structure, data elements are in order, where each and every element is attached to its previous and the next adjacent. However, in non-linear data structure, data elements are attached in a hierarchical manner, that is from one to the next in that particular order. And in a linear data structure, it is always a single leveled stuff, or there's only a single level that is involved. But when we move to the nonlinear data structure, there are multiple levels involved. And when it comes about its implementation, it's very easy to implement linear data structure compared to the nonlinear data structure, which is quite complex to implement. And then in a linear data structure, in terms of getting access or traversal, it is we do that in a single run only. So we can traverse in a single run in linear data structure, but in nonlinear data structure, data element can be traversed in a single run only. And in a linear data structure, memory is not utilized in an efficient way. Not in all of them, depending on how you structure the linear data structure. In some cases, the memory can be utilized quite properly. However, with a non-linear data structure, memory is utilized in an efficient way. And also some examples of linear data structure. We have the stack, the queue, linked list, arrays. While its examples for non-linear data structure included trees and then the graphs. So mostly, if you want to apply linear data structures, they are mostly applied in application software systems. So most of the application software systems that are running on our iOS, on our Android devices, our PCs, in most cases, let me say 100%, let me say 90 to 100% of them uses the linear data structure. However, for applications of non-linear data structure, involves the artificial intelligence that is taking space and then image processing as well. So this new paradigm shift in computing system, the AI's image processing, they mostly use this nonlinear data structure. And then linear data structure are much simpler in storage and manipulation. So if you want to store easily, you can go in for the linear data structure. However, nonlinear data structure are used for representing complex relationship and data hierarchies, as in social networks, file systems, or computing networks. And then for its performance, linear data structure is quite simple, or performance is when we are performing the basic operations we learned earlier, like adding, removing at the end, but they are very slow if we are trying to implement operations like searching and removing elements in the middle, because you need to traverse through the entire list. If there are 2,000 before you can now get the position and then you insert the value in there. However, with a nonlinear, performance can vary on the structure and the operation, but can be optimized for specific operations. So that is that for the comparison between linear data structure and nonlinear data structure. So what is actually a tree data structure? So a tree data structure is a hierarchical structure that is used to represent and then organize data in a way that is easy for first navigation, and the second is for search. So we organize them in a way that makes it easy for us to navigate through the data and also for purposes of search. And it's also a collection of nodes that are connected by edges and has a hierarchical relationship between the nodes. So we can model a simple tree structure as the family structure, where we have the father, the parents, then we have 8 children, and then the parent children will also give birth in that particular order. So that is how you can model a tree data structure in real life situation. And in this scenario, the topmost node of the tree is called the root. That is, in our case, you can say the parent happens to be the root, and the node below it are called the child nodes. And then each of the nodes have multiple child nodes or can have multiple child nodes. And these child nodes can also have their own child nodes as well, forming a recursive structure. So this is a diagram that shows what we're talking about. So we have the parent, which happens to be the one, and it has 8 children as 2 and 3. And the parent children also have sub children, right? More like these ones we have over here. So the root node, which is the topmost node of a tree, or the node which does not have any parent node, is called the root node. Or you could say that the start node, or the topmost node without parent. So in this case, one becomes the topmost node or the parent, and the others follows. So these are some basic terminologies in the tree data structure. We have the root node, which happens to be the starting point or the topmost node. And also we can talk about the parent node as well. So the parent node is the node which is a predecessor of a node. It's called a parent node of that node. So basically any node with at least one child, sometimes known as ancestor node. So these ones are what we call the parent node. Please, are we clear? So the ones in the blue, 1, 2, 3 are parent node.
Hello, sir.
Hello.
So the ancestor node is part of the parent node. I was thinking it's going to be 2 and 3 as a parent node.
Yeah, 1, 2, 3, because 1 itself is a parent to 2 and 3. Abdul Rashid.
Yes, sir. I don't really get the difference between the root and the parent.
You don't get. All right, so
Yeah, you mentioned that the root node is 1.
Yeah, that's the starting point. So the
And
starting point.
Yes, and then the parent is 2. The parent is 2 and 3, right?
1, 2, 3.
So that is where I'm confused, because the 1 is standing there again.
Let me break it down. So before you can be called a parent, all right, so before you can be called a parent, you need to have children. And from this tree we have here, the root node, 2 children. So it's obviously a parent as well, which is 1. Now when we move to the parent, which is 1 at it. All right, so let me repeat. My network just went off small. So what I'm saying that before you can be called a parent, you need to have children, right? So let's consider this tree over here. So this is the root node or the start node. But when you look at it, it has 2 children, which is 2 and 3. So in that point, it qualifies to be a root node and a parent node as well, because it has children. if you look at what we have here, so any node with at least one child qualifies to be a parent node. And this is the root node, which has 2 children, 2 and 3. So it qualifies to be a parent node. All right, so after that, when we move to 2, 2 also has 2 children, which is 4 and 5. So it also qualifies to be a parent. Similarly, 3 also has 6 and 7. So it qualifies to be a parent, right? So if you're talking about the parent node from the graph we are seeing, then it involves 1, 2, and 3. 4, 5, 6, 7 are not part because you don't have any child below them. Please,
okay,
clear.
Hello, sir.
So that is how any node qubits.
Says, does it mean that the one
any node with
the
at
one is
least
double
one
as
child qualifies to be a parent node? So 1, 2, 3.
So please, so does it mean that the one is doubled as a root node and at the same time a parent node, right? Hello, colleagues. Please, is there anyone who can hear him?
I think it's the network.
Several participants left the meeting.
I was thinking it's my network.
We are now 30. Oh. Today the network did not spare us at all.
Seriously,
the
network is very bad.
I'm not even enjoying the class at all. I'm not getting anything.
The network.
Oh.
He can be talking and then he'll go off for some minutes.
Yeah.
We think it's on network and then he'll come back. Now he come back.
He's on different.
Yes. I have similar issue here. I was thinking it's my network that is fooling me.
It's from his end, because if we can speak and hear ourselves very clearly, then it's from his end.
So guys, please, what he's saying is that the one at the top is qualified as the root node and the same time parent node. Is that what he means?
That's what he has come.
Okay.
Yes, Cupid, that's what I mean.
Okay, sir.
Right?
Then I got it. Thank you.
Yeah. Okay. Right. So let's talk about the child nodes as well. So any node with a parent happens to be a child node. So we have the parent, which is this one here as 1, but the rest below it are the child nodes. So we have 2, 4, and then 5 as child nodes. So if we want to take 2, then we could say that 4 and 5 are also child node 4 here. So any node with a parent happens to be a child node. All right, so let's talk about leaf nodes and then, all right, Eric.
Sir, please, can you go back to the slide about the child node? Hello, sir. Hello.
Yes. Yeah, I'll withdraw that one. But I just want to tell you that if
Hello.
you put anybody from the NDC,
Yeah, we can hear you.
Hello.
We can hear you.
I said, please, can you go back to the child node for me to ask some question about the node 2?
Which of the slides? This one here.
The previous one.
Okay.
Yes, sir. Thank you, sir. So about the node 2. So can you say that the node 2 can also be qualified as a parent node?
Yeah, you can see that. Because it has at least a child.
Yeah. Okay, sir. Okay, thank you.
All right. You're welcome. All right, so let's talk about leaf node, or we call the external node. And basically, leaf nodes happens to be any child node. The node which does not have any child nodes are called the leaf nodes. So nodes which doesn't have a child node, we call them the leaf node. Valencia, please, can you mute yourself? All right, so on this particular graph, we have these as the leaf node because they don't have any child below them or under them. So 5, 6, 7, 11, 12, 9, and 10 happens to be the leaf nodes, or what we call the external nodes, because they don't have any child below them. So that's one of the terminologies in the tree data structure. And also we have what we call a sibling. So siblings are children of the same parent node. Children of the same parent node are we call the sibling. So for instance, if you take these two as a parent, then the siblings happens to be 4 and 5. Right. And then we have internal nodes, which are which have at least a child, except the root. We call it the internal node. So except the root, any other nodes, Abdul Rashid. So except this particular parent node. Okay. Except this particular parent node, any other node that has at least one child, we call it the internal node. So from this graph, we have internal node as 2, 3, 8, and then 4. These are the internal node because they have at least one child. And now moving on, we have what we call the neighbor of a node. So for neighbor of a node, that is the parent or child node of that node are called the neighbors of that particular node. So if you look at this particular, taking this particular one as a parent node, these ones qualify to be the neighbor, and these ones are also neighbors. So 2, 4, 5 are neighbors, 3, 6, 7 are also neighbors. And then if you talk about a subtree, any tree of the tree along with its descendants, any tree of the tree along with its descendants, we call it the subtree. So we can take out this one over here and then talk about the fact that this is a subtree of this whole tree that we have. Similarly, we can take this one and then talk about it as a subtree of the whole of this tree that we have. So that is a subtree. All right, so let's look at some properties of the tree data structure. So we have what we call the depth of a node. So this happens to be the count of edges on the path from the root node to the node. And the root node has level 0. And then each edge add 1 unit of level to the path. So it can also be defined as the number of edges in the path from the root of the tree to the last node. So let's consider this tree, for instance, and try to understand its depth, right? And we said this one is 0. So each of the level of each of the edge add 1 to it, right? So now from 0, we move to 3, then we move to 4, and then we move to 11. So who can tell us the depth of this particular tree?
Level 3.
All right, so the depth of this particular tree is 3, right? Because this is 0, 1, 2, and then 3. Or we could count these edges 1, 2, 3 as well. But then you have to make sure you get to the one with the longest, let me see, the longest sibling or child, or the last child that we have. So assuming this one, there was another one over here, then we have to count it as well, right? Then to get the depth of a node or level of a node. So we have level 0, level 1, level 2, and then level 3. So that is the depth of a node. And then we have the height of the node. The height of the node can be defined as the length of the longest path from the... Hello?
Sir, please, the depth of the node is not well understood, because we are talking about edges here. And then, yes, it's like I'm confused, because you're talking about the edges. And once we are talking about edges, I think we count the number of edges, but you're talking about levels also here. So the two, I'm confused.
Yeah, so if you want to get the depth of the node, we use the levels to count them. But I'm saying that to get it very simple, you can use the edges as well. So this is level 0, this is level 1, this is level 2, and this is level 3. But I can use the edges as well. This is 1, this is 2, and this is 3. And to make it easy for you, just use the level. So this is level 0, level 1, level 2, and then level 3. Is it clear now?
Okay, sir. So the levels.
Okay.
Okay.
All right, so let's move on to the height of the tree. Height of a node, rather. So the height of a node can be defined as the length of the longest path from the node to a leaf node of the tree. And the height of any leaf node is always a 0. And the height of node 8 is 1. The height of node 1 is 3. And the height of node 11 is 0. Does it make sense?
No.
The height of any leaf node is 0. The height of any leaf node is 0. The height of leaf 8 is 1. The height of node 1 is 3. And the height of node 11 is 0. All right, so basically we start counting from the leaf nodes. And if we start from a leaf node, it means that any of the leaf nodes, the height is 0. When we move up to the next level, we increase the 0 by 1. So we said for this node 8, it is 1, because we have moved from this 0 and we are now on the second level. Is it clear? So if we are talking about the height of a node, we start from the leaf and then we move upwards, moving towards the parent node. And if we start from the leaf node, it means that the leaf node at 0. If you move a step further, that is going to be 1. If you move a step, that's going to be 2. That's why we say that node 1 has a height of 3. Because from the longest one here, we move from here, this is 0 to 8, this is 1 to 2, this is 3, and then to the 1 itself, which will give us a 3. Right? However, 11 is 0 as we saw from here, and then 1 is 3 as we saw earlier, and then 8, this 8 has a height of just 1. Please, are we clear? So height of a node start from the leaves and then move upwards to the parent node. So you can be given a graph and then asked to find the height of one of the nodes on it, and then you should be able to do that. Now let's talk about the height of the tree. Ambonza Dennis.
Thank you, sir. Please, can you go back to the diagram?
Yeah.
So based on the height of the nodes, taken from the downward, the down, to which 10 is 0 and the 8 is 1. Like I can't see any 2. I can't see 2.
You can't see 2 from
where?
I
can't see 2. If 11 is 0 and the 8 level is 1, so like
the 3 over 2. The 3 over 2, yeah.
There's no indication. Me, I know it's 2, but there is no indication over there. That's why I'm just asking.
No. The examples are just random examples that we're giving. We are not assessing the entire height of each of the nodes.
Like everything we are need to know. Okay, I get it.
No problem.
So I also have a question.
Okay.
I also have a question with this one. The
okay,
arrow, is it must that the arrow should be pointing downward, since this one is the height of a node, and then we said it starts from the leaf.
Yeah, so ideally it's supposed to point upwards from 11, 8, 3, and then 1.
Okay. And then the one we did previously, that one should be from the top downwards, right?
Hello, sir.
Since he's gone.
He's gone. I'm Fonsa.
Yo, my.
Why your eyes? See you.
Exactly, from the top. So this is correct.
Okay, sir. Thank you.
Sir.
All right.
Sir.
Well,
Sir, let me
all right, clear your doubts.
Sir.
Okay, you said the height they start from the leaf, and the leaf is 0.
Yeah.
And it will go up to the parent of the node, and that's where it ends, right?
Relax. Let me clarify this. It depends on a node you are asked to find its height. If it is a parent node, then you can move from this example from 11 to 1. But then if it is 3, you move from 11, 8, and then 3, and then you stop there. Depending on the node you are asked to find its height, that is where you can move from. You can move to.
Oh, okay.
So it's not always the case that you move from a leaf node to the parent. No, depending on the node you are asked to find. Yeah.
Okay.
Repeat the statement again. The statement I just said.
Yeah, so what I'm saying is that it depends. If you are asked to find the height of a node, it depends on the node you are given. Some of the node you might run through from the very last leaf
Sir, so let me bring this example. For instance, if they say we should find the height of
and the one, then
hello,
we can hear you.
I said, for example, if they say we should find like the height of maybe the root 1, you come down to the leaf 11, the 11 leaf there, and then we go up to 8, and then from 8 we go to 3, and then we go up to the 1 to get the height.
Yeah, that's correct.
Exactly.
So depending on the node,
all right.
All right, depending on the node you are given to find its height, that will determine where you will end in your search. Yeah.
All right.
This is a quick question. What? Okay, Eric.
Sir.
So irrespective of the particular node you are asked to find the height, you always start from the leaf. I want to draw some conclusion if I am right, depending the particular node you are asked to find. So you always start from the leaf, or I wanted to know. So I wanted to know if you need to always start from the leaf node.
Yes, you have to always start from the leaf. If you are asked to find the height of a node, start from the leaf and then move upwards. So assume we are asked of 2. And we have to start this one here. All right, so we can be asked to find the height of the tree as well. So basically the height of the tree is the length of the longest path from the root of the tree
to
the leaf node of the tree.
Sir, sorry for interrupting. So the height of the node, for example, using this diagram, this particular diagram, the height of the node.
Okay.
If you are asked to find the height of node 5, do you say 2? Do you say 2 or you say 1? The height of the height of node 5.
Node 5 is 0.
Because we are aware.
Height of node 5 is 0.
Node 5 is 0.
And then and then node 8 is 1.
Yeah. Node 8 is 1.
And 5 is 0.
Yeah.
So 10 will be 0, 9 will be 0.
So
7.
6 and 7 will be 0 as well.
Yes.
Yeah.
Okay. That is fine.
All right. So if we are asked to find the height of the tree, so then we should consider.
So if you are asked to find the height of so from this we are seeing two things over here. We are seeing 2 things over here. Now, when you pick it from 11, then the parent node, that is 1, is 3.
Yeah.
But when you pick it from 5, then 1 becomes 2. When you pick it from 5, because 5 is 0, then 2 is 1. So 1 becomes 2. So in this case, 1 can be either 3 or 2. I don't know whether I'm right. Depending on where you are looking at from, where you are picking it from, depending.
All right, so let me just say this. So you are saying that assume we are asked to find the height of node 1. It could have It could be 2 or 3. That is what you are saying.
Yes, depending on where you.
But
yes, depending on where you are picking it from.
Yes, but ideally, you should start from the very last leaf. And it's okay because you have to capture energy.
Okay, sir. Thank you very much. Good morning.
Okay.
Sir, from my understanding, it says that
okay,
the height is the height of the tree is the length of the longest part. So from this example, if we want the height of 1, we have to first tree the longest part of 1. Then we start from the root up to the top. Hello? Hello, sir, can you hear me?
Yeah, we can hear you. Maybe it's the network's not good.
Hello, can you hear me?
Okay, so what I was explaining is from the note given.
Okay.
If we are to find the height, we have to look for the longest part. So in this case, if we are finding the height of the node 1, we have to look for the longest part of the node 1. Then we start from the root and move to the top.
Yeah.
So from what Lazy is saying, if we are to find the height of node 1, we cannot treat it to 5 because 5 is not the longest part.
Exactly.
Neither can we treat it to 6, nor 7, nor 9.
Yeah.
Because they are not the longest part. So you have to first find out the longest part,
yeah,
start from the root and move to the top. So when you find the longest part and you get to the root will be 0. Then you move up 1, 2 till you get to the parent.
Hello, sir.
Yes. So
right.
Nana,
Thank you
Nana,
so much.
Nana, this will apply to this will apply to only node 1. Because
yes,
only node 1.
Yeah,
because 2, 3, and 4 will have a different height altogether. 2 has a height of 1, 3 will have 2, and then 4 will have 1. So it will only apply to only node 1.
Yeah, that is true. So if it is the parent node, then you have to take care of the longest path in the whole graph.
Okay.
All right. Thank you so much, Nanaji. So let's talk about the height of the tree. And the height of the tree or a tree is the length of the longest path from the root of the tree to the leaf. So equally, we could say that if we are asked to find the height of the parent node, it is the same as telling us to find the height of the tree. So earlier we realized that for node 1, the height was 3. And also in this particular graph here, the height of this tree or this graph is also 3. It's from 1 to 3, 3 to 8, and then 8 to 11. Is that always clear? All right, so let's move on to some other properties. So we have number of edges and degree of nodes. So number of edges basically means that an edge can be defined as a connection between 2 nodes. So if a tree has n nodes, then it will have n minus 1 edges. That is the number of edges. And then a degree of node talks about the total number of subtrees attached to the node. Is called a degree of the node. And the degree of a leaf node must be 0. So a degree of a tree is the maximum degree of a node among all the nodes in the tree. All right, so let's start with edges. And if a tree has n nodes, then it will have n minus 1 edges. So now let's consider how many nodes do we have here? How many nodes do we have in this particular tree? This tree. How many nodes do we have?
So I think 12 nodes.
To find the number of edges, you subtract 1 from the 12, and then we have it. So that is what we have over here. So if a tree has n nodes, in our case, it is 12, right? Then n minus 1 gives us the number of edges that we have. So 12 minus 1 is going to give us 11. So we have 11 edges here. So that is what the number of nodes basically is talking about. And if you want to confirm, you can count the number of edges that we have here to confirm if they are actually 11 or more than that. Please, are we clear with the number of edges? Now let's talk about the degree of a node. So the total number of the total count of subtrees attached to that node is called degree of the node. Total number of subtrees attached to that node is called degree of a node. So let's take this particular tool here, this node here. How many subtrees can we get from this particular tool? Or how many subtrees are attached to this particular node 2?
So
anybody?
0.
Are you
I
sure?
believe 0.
Please, anybody else? How many subtrees can we find from this particular node 2?
2.
Say 2. 2 say.
All right, so it's 2. Right, Eric, it's 2 because if we take this as a tree, 5 and 6 trees. So now those number of subtrees that are attached to happens to be the degree of the node 2. So this is 2, and we have 2 subtrees that are
Sir,
Sir,
is it a node or trace? The 5 and 6, are they nodes or trace?
Exactly.
I'm not getting you.
I mean the 5 and 6 attached to the 2. I don't know. Are they nodes or they are trace?
Sub node or sub tree?
Yeah, so let me see. I don't know if it was in algorithm class. If it was in algorithm class, we could have a null graph, which is a graph that has only one node, right? So ideally, yes, this can be a node, or preferably you can call these ones nodes. That is quite okay. But then if we are talking about subtrees, then we could say that these are subtrees under this particular node 2. Please, are we clear? Prince.
Sir.
So me, I was thinking that maybe the subtrace would be like the two siblings, and like two. Apart from the two, we have three, and then for their siblings, will be the subtrace. That was what I was thinking first.
Yeah. So a subtree is every part of the tree. So we can take this as a subtree. We can take this as a subtree. We can take this as a subtree as well.
Okay, so that's how I got it.
Please come again. You said a subtree is what? You said something right now.
Right. So we are taking this one as a subtree. And now, Valencia, I didn't hear you.
You made a statement right now. You said a subtree is. I didn't really get it.
I also forgot to know.
No,
so,
you
earlier on you said that the earlier on you said
yes,
subtrees are any node of the tree along with its descendant. That's what we discussed earlier. Subtrees, any node of the tree along with its descendant.
Subtrees, and I'm saying yes, preferably they can be called nodes. However, if you want to go by the subtrees, then this can be a subtree. This can also be a subtree, and this can be a subtree. But if you take this particular node here to determine the number of degree or the degree of the nodes, then we have to consider how many subtrees can we get from this particular two, or how many nodes are connected to these two. Then it will help us to note or get the number of or degree of the node. So I was saying that yes, you can call these ones as nodes, but then you can equally call them as subtrees as well. Prince.
Hello, sir. Okay, from my understanding, the trees are formed from the nodes, right? So before you become a parent, you once be a child to someone, and that flow will then come down until we get the nodes. So the trees are gotten from the nodes.
Exactly. So equally, we say these ones are subtrees, but then preferably, as I said earlier, we can call them nodes, and that's okay. And even these ones can also be called a leaf node as well. Eric.
So I'm really confused about the nodes at the left-hand side. So from the nodes
where? Here. Okay, here.
You
mean this? You see nodes or nodes? Which of them?
The degree of a leaf node must be 0. So I was confused about the 5 and the 6 nodes. I believe there's 5 and the 6 are leaf nodes.
Eric. And don't jump the gun. Let's move step by step. We are trying. So we are trying to understand what we have here. Before we can now move on to the next. So please let's understand it step by step. So first we are trying to get a degree of nodes. We are trying to get a degree of the nodes. And I'm saying that before we get a degree of the node, we need to count the subtrees attached to a particular node, right? And now this is a subtree of the entire tree that we are seeing. Now let's take this particular node here. How many subtrees are attached to 2? We have 5 and 6. Yes, ideally 5 and 6 are supposed to be nodes, but they can equally be called as subtrees as well, because Prince made an assertion that before you become a tree or a parent, you need to, before you need to be a child before. So these ones can also be subtrees. But then we can preferably call them. So what is fine, which is 2, 5, and 6. Of node, which is 2. All right, so moving on to the next part, which happens to be the degree of the node must be 0. That means there's no subtree attached to 5. Neither there are some attached to 6. So their degrees are obviously 0. And that is what we mean here. So leaf node doesn't have subtrees or nodes connected to them. So obviously 0. So I know the confusion is coming from subtree and then the leaf node. Yes. From these two, we can have subtree 5 and 6. But you can call them nodes as well. There's no problem with that. But then to be able to get a degree, we have to find the subtrees that we can get from a particular node. And then you can move on. But then if you want to go by the node, then you might say these are not subtrees. The entire tree just didn't give it to us. And actually your hand was up.
Okay, sir, thank you. Sir, I wanted to know, or I wanted to get it clear that a node can be a subtree to another node. As far as that node, let's say A, has other nodes under A, then A can be, the other nodes under A will be called subtrees, although A is a node.
Yeah.
Okay, thank you very much.
Yeah. All right. Please, any other question?
Sir, so on this note, the degree of node 2, we are saying it's 2. Are we saying it's 2 or we are saying it's 0? It's 2.
It's 2 because it has 2 subtrees under it.
Okay. Okay, and then the degree of node 3. What will you say? Will you say it's 2 or it's 4?
Which one?
The degree of node 3.
Okay, so how many subtrees can we find from node 3?
I'm seeing 4.
That will be 4.
Yes, so that is 4. Is it clear? But then
it's clear. Yes, there's a statement. The degree of a leaf node, okay, must always be 0. Okay, all right.
Yeah.
Okay, get it now.
And that is not just all, because now we found that 2 has a degree of 2, 3 has the degree of 4, and equally 4 also has a degree of 2. But then we are asked to find the degree of a tree. So basically we take the maximum value or the maximum degree of a node among all the nodes in the tree. That's going to be the degree of the tree. Please, is it clear? So instead of taking 2,
come again.
All right, so we said earlier that this particular place, this 2 here, has a degree of 2. This also has a degree of 4, and this one also has a degree of 2. So if we are asked to find the degree of this entire tree, then we have to pick the one with the maximum value, which is 4. And then say that the degree of this tree on the screen is 4, and not 2 and then 2, because we are picking the highest and then talking about it. So this is what we have over here. So this particular description over here, the degree of a tree is the maximum degree of node among all the nodes in the tree. All right, so let me go to what's Prince.
So this side, I'm a little bit confused because I was thinking we are going to count all the nodes under 1.
I hear you.
Hello. I said it.
Hello.
I was thinking we are going to count all the nodes under the node 1. They can't hear me.
We can hear you
network
clear.
is breaking.
His network is not good.
Okay, but I guess the question he wants to ask. So he wanted to say that we probably have to count the number of nodes that we have. Yes, so if we are to consider this particular node hello? Please, can you hear me?
Yes, sir, we can hear you.
All right, so he wanted to say that we are counting the number of nodes that we have in the tree, and then we talk about it. Yeah, but that is not the case. So we basically, let me read this one for us to see. The degree of a tree is the maximum degree of a node among all the nodes in the tree. So yes, this particular node has 2, this one also has 4, and this one has 2. So the maximum degree, or the degree of this tree, is 4. Because amongst all the nodes, the maximum one is 4. If you move to 5, 5 is 0, 6 is 0, 7 is 0, 8 is going to give degree of the tree. That's all. Please, are we clear?
Yes, sir.
Oh, okay. So the degree of a tree is different from the degree of a node. Is that it?
We don't count the node, the parent node. So a circle node, I mean the only node has a circle. That is this particular one here, which is figure 1, is a circle. So we don't look at as there's no root here. This is to confirm what I was saying earlier here, that we can consider 5, 6 as trees. One of the parents before you get siblings. So you can stand alone and then later get siblings as well. So in figure 2, node 3 has multiple parents on different levels. And in figure 3, it has multiple parents as well. And then disconnected components, which is in figure 4, there are 2 unconnected group of nodes. And that is what we have over here. All right, so let's talk about trees, types of tree data structure that we can have. So on the basis of number of children, that is how we can determine the type of tree data structure. So we have the binary tree, we have the ternary tree, and then we have the n-array tree. And the binary, as we know in a basic computing, zeros and ones. So it has at least, is it at least, at most two
exactly two
subtrees, or let me say not exactly 2, but at most. That is a binary tree, at most. So you can have a node which has one child node, that is acceptable. But you cannot have a node which has more than 2 nodes, that is not acceptable. So the node should be exactly 2 or below. That particular tree qualifies to be a binary tree, not exactly 2, but then not above 2, but then below 2 is acceptable. Please, are we clear?
It can be 0 2, right?
Or it can be 0.
And still qualify as a binary tree.
Yeah. So the issue is that it should not be more than 2, sorry. It should not be more than 2. So 0, 1, 2 is enough to qualify it as a binary tree. And then we have the ternary tree, which has 3 as well. And then we have the n-array, which can take any number of subtrees or subnodes or children under a particular node. So this one, for instance, you said it can have 0. Well, this qualifies to be a binary tree, but then the last one, which are the leaf nodes, have 0 siblings, children attached to it. So if this one wasn't there, still this is qualified to be a binary tree. All right, so let's look at some application of tree data structure. So one of them is file systems. So most of the file systems that we use, like a file manager, most of them are implemented using the tree data structure, which allows for efficient navigation and organization of the files. And also, if we want to talk about data compression, we can equally use trees to perform data compression. And one of the examples is the Huffman coding, which is a popular technique for data compression. And this involves constructing a binary tree where the leaves represent character and their frequency of occurrence. We saw the Huffman encoding in the algorithm class. And after that, when the binary code are written, the resulting tree is now used to encode the data in a way that minimizes the amount of storage required. And then compiler design. So in compiler systems, a syntax tree is used to represent the structure of the program. So those of you who write in C++, your C++ compiler was written in this particular style. And also with database indexing, B-trees and other tree structures are used in database indexing for efficient search and data retrieval as well. So we'll talk about graphs later on, but then for some applications of trees, we can equally talk about graph theory. So in trees, we can find some concept of graph theory to represent hierarchical relationship between objects, maybe network nodes, topologies, and solve other related problems in network routing and some connectivities. And one popular example is the minimum spanning tree, which is often used to find the shortest path for connecting nodes in a network with minimum total edges. So if you are given this particular tree here, for instance, we can use the graph theory to be able to construct minimum spanning tree from this particular graph that's been given to us. And then in computer programming as well, trees can be used to effectively or efficiently store, organize, and manipulate data. And then some of the common data structures include the binary search trees, which are used for searching, insertion, and then deletion of element as well. And then we have the heaps. We'll talk about the heaps, I think next week if there's enough time, which is for implementing the priority queues, which are essential for tasks like the scheduling and graph algorithms, such as the Dijkstra shortest path algorithms. And we have the trie, which is mostly called a prefix tree, used for efficient storing and searching strings as well. We have the segment tree, which is used for efficient answering range queries, such as sum or minimum of element within range in an array. And then we have the suffix tree, which is popularly used for string and pattern search in text processing and computational biology. And this is I think we saw this also in the algorithm class. So in searching and sorting as well, we can use trees in various ways. So examples include a binary search on a sorted array, and then a tree-based sorting algorithm like the heap sort and then the team sort as well. So in search, we can use the binary search and also the tree-based sorting. We can talk about the heap sort and then the time sort as well. Moreover, in artificial intelligence or machine learning, we can talk about decision trees, which are mostly used for classification and various regression tasks in supervised learning, where the algorithm will learn from a labeled dataset to make decisions or predictions. And then also we have the game trees, which are used in adversarial search, and also game playing algorithms such as the minimax algorithm to represent possible moves and alternate outcomes as well. So in a similar fashion for artificial intelligence, this is how we can model a tree. So assuming you apply for a job, and then you can write an algorithm more like this in the form of a tree. So salary is between $4,500 to $7,500. Then you can build a tree out of it. So you have a yes option, you have a no option. So if you say yes option, All right, so in either scenarios, you build a tree at a far end. So that is what we are seeing over here. So if this is the start of all right, so this is the start of the graph. So we start from here. So if the salary is in this particular range, all right, so any choice that we make, we try to take track of it at this point. So we have the min max.
Hello, sir.
Hello.
Sir, please, I'm not following. I don't know whether because of my network or yours. Like, you go off for some time and then you come and then you continue. Like, I'm not getting it.
All right, please. Is this the same for everybody?
Yes, sir.
Yeah.
Please, your line keeps breaking.
All right, let's start all over again. So what I'm saying is that in AI system, for instance, we spoke about decision trees, and this is how the decision tree is being built in an AI system using the tree structure, right? And this is more like you apply for a job and you want to build a tree to accept the offer. So now you start with the salary range. If it is between 4,500 or 7,500, there's a decision for you to make. And the decisions are only two, either yes or no. So if it is a yes, so this is what we have here. So this is the decisions that we can make out of this condition. So if it is a yes, we move on to the next, which is what we have here. If it is a no, we move on to this particular place. And then at this condition also, we have to make a decision. Is the offer near to my house or the home? Then also you can make a decision out of that. If the offer is near, then I'll probably accept it. If the offer is not near, then I'll discard it. I will decline the offer. And then you do this process until the final decision over here. Finally, if they provide a cab facility or a cab facility, if there is no cab facility, you decline the offer. If there is, you accept the offer. So you do this to build the tree structure, where these are going to be the parents and these are going to be the siblings out of the decisions that you made earlier. Please, are we clear? And these are the arbitrary values that are assigned to every decision or every issue. And at the end of this, you can now add these ones and then make up the decisions that you have taken. But mind you, these are the features that the algorithm will learn from. The decision tree algorithm will learn from, and then when you provide all of this information, then it will not give you the outcome as well. So this is how the structure is being built in a system like the decision tree in artificial intelligence. So each of the decisions given to it builds a tree, and then out of it, it predicts the outcome, whether to accept the offer or decline the offer for you. So this is how the trees can be used in AI. Qubits.
Hello, sir. Please, where from the numbers that we are seeing in a tree?
I didn't hear you.
The number that we are seeing there, like how do they get it? I can see 1 minus 3,
Yeah, that's what I'm saying. They're just arbitrary values. They're arbitrary values that are just assigned to each of the options that you make. Did you hear me?
Yes, sir.
All right.
Please, colleague, is there anyone who understood the thing? Who can explain it better for me?
All right. Anyone to explain it for qubits? Probably I didn't explain it quite well.
Yeah, let me try.
Prince.
Okay, qubits.
All right, try.
All right. The diagram at your left hand side, from my side, the left hand side. That says the first one, that says the salary between this. Assuming like you want a job, and the job, you have conditions that you need before you will accept the job from any company. And the first condition is that the salary should be between the amount over there. So you first check if the amount is between them, you accept and proceed to the next condition. Is the company closer to your house or your home or the office? If it is yes, you proceed. If it is no, then you decline the job. And you come down again. Do they provide a cap facility? So those ones are just your conditions. So if they provide a cap condition, then you accept what? The offer. So it means that you only accept the offer if the three conditions are being met. Hello, sir.
Hello. Yes, that's very true.
Clear.
And then
it's clear now. Out of the
so in a computing system, you as a human being understand, all of these ones here. But then the computer have to model it in a tree form so that to understand what you actually want, or will learn from the information that you have given to it. That is when it will represent all of these as a tree. Right, so that is basically how the decision tree algorithm really works. That's basically all.
Okay, so does it mean that the right hand tree is the assumption done by the computer itself?
Exactly. Yeah.
Okay.
Yes.
Thank you.
Okay. Is there any other question? All right. So as usual, let's talk about some basic operations of a tree data structure. So we can create a tree. We can insert data in a tree. We can search where we are looking for specific data in a tree, whether it's found or it's not found. We can equally traverse, and I'm very sure we know traverser, where we spoke about the DFS in algorithms, and then under the DFS, we talk about the in-order traverser, pre-order traverser, and then the post-order traverser. And now we have the breadth first search as well, which is level order traverser. So let's talk about them in detail. So for BFS, we said it's a level search process. So we have level 0 over here, and right after the level 0, we go to explore all of the nodes and the level. So explore that one, and go to the next level, which is level 1, and explore all the nodes there. So to level 1, we have A and then B. So we explore all of them. When we are done, we move on to explore the nodes at level 2. So we have C, we have D, we have G, and then we have H. After exploring all of them, we now move to the next level, which is E, F, and then I. And then when we are done, we explore the final level here, which is level 4. And then that is basically how it works. This graph looks very simple, but sometimes the various nodes are quite messy. But then this is just to demonstrate how the BFS really works. However, the DFS searches depth-wise. Mostly the left first before it comes to the right until all the various nodes are exhausted. And in this particular DFS, that is where we have this concept of backtracking. In some cases, you reach a dead end and your search, you couldn't find the value or the element you are searching for. However, you haven't exhausted all the nodes in that particular tree. So you have to now backtrack to the previous one you visited before you move on to the other one you haven't visited. So this is how it's being done. So instead of we doing it level by level like this, we go from the parent node or level 0, we move to the first node to the left of level 1, and you go to the first node on level 2, the first node on level 3. Now we move to the other node, the last node on level 3, move to this, and then we move to this one. So when we get here, we haven't explored H, I, J, and K. This is where the backtracking comes in, and this is where a specific data structure you're using comes in here. And from the algorithm class, we knew the data structure that you're supposed to use in a DFS algorithm. Please, who can tell us?
Yeah, the circular.
You are listening. Who can tell us from the algorithm class what data structure is efficient for this particular DFS algorithm or search? Anybody?
Graph data structure.
Yeah, this is a graph data structure, but we want to search this graph data structure. But in the process of searching, we need to store the various nodes that we have visited and those we haven't visited. And we cannot do this efficiently using the graph data structure. There's an alternative data structure we can use to do that. Anybody? Yeah, anybody? All right, so that is the stack, right? For us to be able to efficiently get the backtracking to work for us, we need to use the stack data structure to be able to do that. So if you use the stack, it will tell you which nodes have we gotten to, and then the backtrack will just take effect just like that. Please, are we clear? So if you've forgotten your algorithm class, please just go and look at how the DFS works, and then you understand it more. So let's look at the various types of traversal in BFS. So we have the level order traversal, as I just explained earlier. So we move to 5, then we explore all level 1, which is 12 and 13. We move to level 2, we explore all of them. Move to level 3, explore all of them. So this is how the order is going to be. So 5, 12, 13, 7, 14 in that particular order. So this is how the level traversal for BFS really looks like. And now for DFS, we have the in-order traversal. And for the in-order traversal, this is the rule. So we have left, roots, and then right. left, root, and right. That is for DFS in order. Left, root, and right. So the initial node here is this particular one we have here. So we have left, roots, and then right. So this is the left that we have. Then you go to root, go to right, you go to root, then in this particular order. Please, are we clear? So this is how the in order traversal will look like: 4, 2, 5, 1, 3, and then 6. This is in order traversal. Please, are we clear? So left, root, right. Left, root, and then right. All right, so is the pre-order. So the pre-order is roots, left, and then right. And the pre-order is what we are quite familiar with. So we have the root, which is this one over here, and then left, then we go to left, then we go to this, and then you go to root, then you go to this one, and then this one here. So this is the pre-order traversal, and the other one was the post-order traversal. So just notice how the various order really works. So if it is a pre-order, then you have the roots, the left and the right. That you start from the root node, you move to your left before you go to right to get the traversal right. Now we have also the post order, which is the left, right, and then root. Left, right, root. So we start from 1, however, 1 will not be explored. So we explore the left of 1, which is this. Then we go to right before we go to the root. Then we go to right before we go to this, and then this one here. So when you go to 6, the root of 6 is 3, and then you move to 1 over here. Please, are you clear? So if you note the left, right root, it's quite easy to follow. Is there any question? I hope we are following.
This one they said it has passed my eyes more.
Right, so let me just start all over from here, right? So what I'm saying is that this is mostly for DFS. We have the qubit. Your hand is up.
So sorry, it was the
right,
last
so we have the okay, so we have the left, root, right order operation for in order traversal. So left, root, and then right. So instead of us starting from the root, we will start from the root order, but then we will not add the roots element. So here, and then move to this particular left, last, the leaf node. And then we go to each root, which is 4 to 2. Now we move to right, which is 5. Then we go to the roots, which is 1. Before now you go to right, there's no left, so we proceed to right again. So this is how the in order works: left, root, right, left, root, right. All right, and then also the pre-order is root, left, right. And then we start from our roots, which is 1, we move to 2, which is left, we move to 4, which is also left. Now at 4, we move to right. We move to right again because we already visited the 1, and then we move to right. Mind, when we go to 3, there's no left also. That is why we didn't go to left. We just went straight to right, which is 6. So the order is going to be 1, 2, 4, 5, 3, 6 for pre-order traversal. Now let's move on to the post order. The post order is also left, right, and then root. So you have to notice that if root starts, then the root element is going to be part, or whichever value that starts, its element is going to be first. So this element is going to be first. Before we move to right, then we go to their roots in that particular order. So when we get here, we are starting from the parent order, but then the parent is not going to be part because we are sitting left. So we move to the left, which is this particular node over here. And then the traversal says right. So you go to right, which is 5. After right, we are asked to go to the roots. So the root of 4 and 5 is 2. Right. And then after right, we now go back to this right because we are from the roots. You're supposed to go back to left, but left is not there. So we have to go to right, which is what we have. And then we go to right, then finally we get to the roots as well. So if you notice the order is quite easy to follow. So left, right, roots, and then you are good to go. So whichever that starts first means the element is going to be part. So if root starts, means the root element is going to be part or starts before you move on to the next as well. All right, so let's talk about another concept, which is this.
Sir. Yeah, please, can you go back to the
which of them?
The previous slide. Yes, so the order is left, right, root. Now the left per the diagram from 1 you move to 4.
Yeah.
Is that not it? Why not moving to 2 first before 4?
Why not moving to 2 first before 4?
Yes.
Yeah. So
from one.
Yeah, speak. I'm listening.
Yeah. So I wanted to know because it's left and right. So if it's left, the first. Okay.
So we are moving to the leftmost of the node, which is more like the last value to the left of the node, or the last node to the parent node. That is what we are considering, not the immediate left. Is it clear? So the initial traversal route to the leftmost, that is the last node. Yeah. So this is 1, and its last left node is the 4. That is why we started from 4, but not 2.
Then you move to right. That is 5.
Yeah. Then you go to
then
roots.
From right, 8 roots.
Yeah.
That is 2.
Yeah.
Then from
so
there,
supposed to go to left,
they say,
but we have left already. So we have to move to right.
Right. The rightmost.
And
that is
6. And then from right, you are supposed to go to roots. So the root of 6 is 3.
It's 3. Okay.
Right. And then move to
there. From the root, you go to the left, which is 1.
Left. There's no left, so you just have to move to the root.
Okay.
Yeah. So this is how it basically works.
And then please kindly kindly go 2 slides back. Yes, then the kindly go back. Yes, with this one. And this one is 2 is no.
This one?
No, the one before this one. Okay, so this one.
Okay.
Yes, this
in order.
Yes, the in order.
Okay.
So this one to it's left, then you go to the root.
Then right.
Okay. Then there's no left again. So you go to No, from 2. It is left, that is 4. Then root. From left, you go to the root, that is 2. Then you go to right. So from right, where do you go?
You go
from
to
right
left.
here, where do you go?
You go to left.
So in this case, the left is the 1.
There's no left.
There's no left. Yes.
So you move to root, which is this.
Okay. I said, why is the root not 6?
And then you move to right, and then.
Say, I'm
listening.
So why from 5? That is right. From 5 is right. From right, we are supposed to move to left, but there's no left. So we move to the root.
Yeah, so you move to root. Yeah.
The root of which one? Because we are supposed to 6 has its root to be 3. Is that not it? And 3 has its root to be 1.
Yeah.
So why not 3? And why not we go to the parent root? That is the 1.
All right. Let's go through together. So you see. So we start from the root, the leftmost, right, which is this one here, 4, right, which is left. So now move to the root of 4 is 2, which is this one here. Now move to right, which is this one here. But we are asked to move to left again, but this is a leaf node. It doesn't have any value. So we move to root. Yes, ideally the 5 doesn't have the root. The root of 5 is 2, but 2 has been visited. So you have to move to right, which is this particular one here. Then we move to root. There's no root, so we move to right, and then we move to 6. Right. Yes, I know it's confusing, but then when you sit down to understand the left root right and the root left right and the left right root, you get to understand it better. All right, so let's talk about the spanning trees, which we came across in the algorithm class. The spanning tree is basically a subgraph of an undirected connected graph. This condition is very much important. Undirected connected graph, which includes all the vertices of the graph with a minimum possible number of edges. And one thing is that if a vertex is missed, then it's not a spanning tree. If you miss one of the vertices, it's not a spanning tree. And also the edges may or may not have weights assigned to them. So the edges might have weights assigned to them. All right, my network. different of. So you can see that S. So the total number of spanning trees with n vertices that can be created from a complete graph is n minus 2. So for instance, if n is equal to 4, the maximum number of possible spanning trees is 4 raised to the power 2, which is going to be 16. And the n happens to be the number of vertices that we have. So let's take this particular graph here, for instance. How many spanning trees can we get from this particular graph? A, B, C, D. Who can help us? How many spanning trees can we get from this particular graph? Or before that, how many vertices do we have? Or how many nodes do we have?
4.
It's 4.
All right, so a possible
So I can't hear you.
trees you can get from this is 4 raised to the power 2, which is 16. So if we are connecting small, what I'm saying that if we want to construct subtrees from this particular tree that's been given to us, we are going to get 16 of them.
So the calculation, how did you get the 16? Because per the formula up there, we are not going to get 16. I don't know whether we are applying the formula up there. Because it's n into bracket n minus 2. And if it's n is 4,
Hello, please, can you hear me?
Yes, sir, we can hear you. But a colleague is asking about how we got a 16 from. Look at the formula that we have at the top there. N bracket opening n minus 2. And then
it's n raised to the power 2, not n minus 2. So it's just n exponent 2. N exponent 2. And that is going to be where the n is the number of vertices that we have in the graph, or the number of nodes that we have in the graph, or the tree. So it's n raised to the power 2.
Oh, okay. So the n minus 2 is the power, is the index, is the power. N minus 2 is the power.
N minus 2. So this is n raised to the power 2. And then I'm going to get 16. So if you are to extract or construct subtrees from this, you're going to get 16 of them. So maybe after the class, we can try to see if you get 16 of them.
I'm not getting the formula.
Sir, please,
Sir, the formula.
Please
The
write the
formula
formula.
is confusing.
Sir, write the formula. Use your red pen to write the formula. Well, for us to see how the formula is. What the formula? We want to see how it is. The formula. Yes.
Yeah, the formula is
write
confusing though.
For us to see.
Because if it is 5, then it means that 5 into bracket 5 minus 2.
Yeah, so it's n raised to the power 2.
Okay.
So that is all about the formula. The formula is n raised to the power 2. That's all.
Yes. And Dennis.
Okay, sir. So I was thinking like the n is like n, and the powers will be like n minus 2. So if the nodes are 4, it's going to be 4. Then the power of n, which is 4 minus 2, will be 2. Then 4 raised to the power 2 will be 16. I'm thinking that way.
Then that is what I was also saying. That if that is the case and it is 5, it is not going to work.
Which one is 5?
I also have the same thought. Yes.
No.
No, like if the number of nodes are five, then it means that it would have been n 5 raised to the power 5 minus what? 2,
Yeah.
which will be 3.
Yes.
So it will have been 5 raised to the power 3.
Okay. Yeah.
Yeah, so it is n raised to the power 2. If you want to find the total number of minimum spanning trees you can get from a given graph or a given tree, is n raised to the power 2. Right? So for instance, this one we have here, we have 1 vertex, 2 vertex, 3, and then 4. So 4 exponent 2 give us 16. That means we are getting 16 spanning trees from this particular tree given to us. And as I said earlier, you can try and see if you are going to get 16 or less, and then you confirm for me next week. So these are some examples of the spanning tree you can get from a previous graph. So we have 1, we have 2, we have 3, we have 4, we have 5, we have 6, and many others that we can get. So these are just some examples that I just displayed. Please, are we clear?
Yes, sir. Sir, please, can we go for some 15 minutes break?
Moving on, we have.
I don't know whether it's possible.
You want a break? Should we go on a break, or we should continue for 30 minutes and close? Because I'm tired myself. The network hasn't been okay for me. So which is which?
Okay, let's continue. If it's 30 minutes.
So let's continue. Let's continue and then we'll close.
Okay. All right. All right. So we have the concept of minimum spanning. Minimum spanning tree. We have a concept we call minimum spanning tree in the tree data structure. And when we talk about minimum spanning tree, it's a spanning tree in which the sum of the weight of the edges is minimum as possible. Earlier we said that the spanning tree can have either weight or no weight. But then if we are talking about a minimum spanning tree, means the tree must have weight assigned. So we have this tree, previous one, but then now we assign some values to the edge. So we have 4, we have 5, we have 2, and then we have 1 here as the weight that assigned to it. So what are we trying to do with the minimum spanning tree is that if you're able to construct all the 16 possible spanning trees, when we add all of them their weight, then we have to take the spanning tree that gives us the minimum sum of the weight. That becomes the minimum spanning tree. So now think about it. If you are giving an exam and asked to find the minimum spanning tree, what is the approach? How do you go about it? Anybody? Let's assume we are given this particular tree here with the weight and asked to find the minimum spanning tree. How do you go about it? Do you have to draw all the spanning trees and find the weight?
No.
Elliot,
You look for the yes, sir. You move in the direction of the place where the weights are less.
I couldn't hear you.
I said you move in the direction where the weights are less. The possible weights are less.
Okay, so you move to the direction where the possible weights are less. All right, thank you so much.
Yeah, so let's say you are moving from A to C. When you pass from the node A to the node C, then I will pass from B B weight is 4, and from B to C weight is 1, so that will be 5. But when I pass through A to D, that one is 5, and D to C is also 2, so that one is also 7. 5 and 7, 5 is less, so I'll pass the A, B, and C.
Okay. All right. Thank you so much. Now, from this particular tree, this is a spanning tree you can get from here. So we have a minimum spanning tree. So we have this one as one of them. And each sum of the weight is 11. Similarly, we have this one also. And each sum of the weight is also 8. We have this one also, which has a sum to be. And we have also which has sum to also be all the sum. Then choose this as a minimum spanning tree because it has a list.
Thank you, sir. I think the minimum spinning that you show the first one.
Which this one?
Previous, yes, please. I think this one is a complete listing. It's a complete. So is it that when you are trying to run through, automatically one edge will be out? I don't know whether.
Yes. So for a spanning tree, you have one less of the edges compared to the complete graph or complete tree. At least one layer, but all the various vertices must be included. So if there are 6 vertices, all the vertices has to be in any of the spanning trees, but then the edges, one of them will have to go.
Oh, okay.
Yeah.
Okay. Yeah, I get it.
All right.
I get it.
So these are examples, and you realize that all the vertices are present in any of these subtrees, but then it is shortened of one edge. So as I was saying, assuming that all of these we have happens to be the minimum span, the spanning trees that we have. Now we look at the ones that have the less sum value, and it's going to be this one, 4 plus 2 plus 1, which is 7. So this is going to be the minimum spanning tree from the tree we saw earlier. Is it clear?
Yes, sir.
All right, so these are some use cases of minimum spanning trees. So for computer network routing protocols, and then civil network planning, you can use the spanning trees to be able to do that. And for minimum spanning tree applications, if you want to find a path in the map, you can use the minimum spanning tree. And also, if you want to design network like telecommunication network, water supply systems, and electricity grids, these are the concept that we use in the route the least current to the various houses or the various nodes or vertices which happens to be the household that we have, and also to supply water from the various process. But then in this process, when we talk about spanning trees in algorithm or computing systems, we have algorithms that are used to if you ask find the minimum spanning tree from this particular one, how do you do it? And then Elliot said that you start from one of the nodes and then you move in the direction of where the weights are quite smaller. But come to think of it, the computer doesn't have the eyes to know that from vertex A to B is shorter than A to D. So how would the algorithm be able to know all of this one? So that is where we have these algorithms that are going to be able to determine the edge that is least or the vertex that is least from the other. And we have several of the algorithms, but two most popular ones are the Primus algorithm and the Kruskal algorithm as well. So the Kruskal algorithm is used to find a minimum spanning tree of connected weighted graph. And Mr. Dennis.
I think some question just dropped inside this one. So it'd be like maybe in exams or maybe in a test, they are saying that list the or determine the minimum this one spinning tree.
Spanning
so
tree.
Is it that spanning tree? Is it that you're going to list all the possible minimum spanning tree before you indicate that okay, this is the minimum spanning tree? Or you just go straight ahead?
Okay, so let me clarify this. We have spanning trees and minimum spanning tree. The minimum spanning tree is just one out of the many spanning trees that we have. So probably in an exam, if you are given a tree and asked to provide a minimum spanning tree, that one weight has to be assigned to the edges of the minimum spanning tree. So it's going to be easy for you to just draw the spanning tree and put it there. That one is quite okay. But then I don't think they will ask you to draw all the spanning trees and then indicate which one is the minimum spanning tree. That will be difficult unless maybe the edges are just 2 or 3. Because if they are 2, if they are 2, you get only 4 minimum spanning trees or spanning tree. If they are 3, you might get maybe 9 or so. Yeah, 9. So that one is easy for you to draw, but 16, 32, and those ones are too much. So you only be asked to draw a spanning tree or find a minimum spanning tree if the graph has less edges. Right. So
okay.
in exam situation, yeah, that is how it is. So we use the Kruskal. You're welcome. Kruskal algorithm to find a minimum spanning tree of connected and weighted graph. And basically, for such spanning tree, it should have every vertex. The spanning tree should have every vertex of the original tree. And then the total weight of all the edges in the tree is less than or equal to the spanning tree. Right? All the vertices must be present. However, the edges must be one less or equal to, depending on the structure of the graph. But since it's a connected graph, then the edges of the minimum spanning tree should be one less of the original tree that is given to you. All right, and then so let's talk about the Kruskal algorithm. So this is the steps that the Kruskal follows to be able to determine the spanning tree from a given graph. So the step 1 is that all the edges of a given graph, which is G, V of E, are arranged in a non-decreasing order in accordance with the weight of the edges of the edge. It is arranged in a non-decreasing order in accordance with the weight of the edges. So this is how the algorithm will start. And now the smallest weighted edge from the graph is chosen and is checked if it forms a spanning tree earlier. So one thing you have to notice is that Kruskal takes the edges and then compares to see if it forms a spanning tree. Remember, a spanning tree should not be a circle. So if the edge is about form a circle, you have to discard that edge and move on to the next and pick up the next edge. If there's a circle, it is discarded, as I said earlier. A spanning tree should not be a circle. So if the smallest weighted edge is picked, then it's about to be appended or added to the spanning tree, and you realize that it's going to form a circle, you discard it. And then you repeat step 2 and 3 until v minus 1 number of edges are left in the spanning tree. And then you are good to go. So this is the steps in which the Kruskal algorithm follows to give out the spanning or minimum spanning tree. And mind you, the minimum spanning tree should have edges, and the edges should have weights as well attached to them. So this is how the Kruskal algorithm basically works. So given this particular graph here, we are then asked to use the Kruskal to demonstrate how we can get the minimum spanning tree from it. So we have the edge name. So this is edge 1, this is edge 2, this is 3, 4, up to the last one. And each of them have weights. This is 20, this is 9, this is 13, this is 2, this is 1, this is 4, this is 3, 14, and then 5. So we've numbered all the edges, and then we've assigned the various weight to them. Now this is how it really works. So this is the edge number, and this is the vector pair AB. Edge number, this is the vector pair AC, and this happens to be the weight. So this is how it's going to be stored in the computing system, and then it will pick one of the edges, the least one. So in this scenario here, it is going to pick the least edge, which is E4, and then try to form the minimum spanning tree. If there's any case where this E is forming a circle, it will discard it and move on to the other. But then since this is the first edge that is being picked, obviously it won't form a circle, so it will be placed in a plane, or this BC vector pair, vertex pair are going to be kept. Now it will move to the other one, which is the least, which is E7. So to pick edge E7 and then try to form the minimum spanning tree with this one over here. Right, so if it is not forming a circle, then it will add it to the minimum spanning tree and move on to pick the least, which is 3 here, and then after that 4, and then 5, then 9, 14, 13, 14, and then 20. So if any of the edges that is being picked is forming a circle, it will discard it and then move on to the next. So that is how the Kruskal algorithm basically works. Are we clear? And then after that, you see the edges are being arranged, the weights of the edges are being arranged in this particular order. And I think we have a demonstration here. So this is the first one that we have. So it will pick AB as the first. That is what we have here. Now to move on, and then we'll pick this one as well. And then it will pick this. And also, which one is it? I think it will pick this. And now come and choose the 9, right? And then that is basically all. So this is the minimum spanning tree we have here. So the edges that are not when you try to add any edge that is not here, it's going to make this form a circle. So we will not include it. So the graph given earlier, this is the minimum spanning tree that we have. Please, any question? Please, any question or any clarification?
So it must not form a circle.
Yes, so minimum spanning tree does not form a circle. So if you look at the notes, the simple note here, after adding edge E6, we don't have to add E5 since it forms a circle.
Yeah, to form a circle.
Is that so? Any edge that forms a circle, we have to discard it. And I hope we know circle. So when you start at one of the nodes, so let's take this node here. You're not supposed to be able to turn back to it again. Right? So we can move and then we get the dead end over here. But if this forms a circle here, we can move from here and go to this side, go to here, and then come back to where we started. So a minimum spanning tree or a spanning tree is not supposed to form a circle. Or a greedy algorithm that is used to find the minimum spanning tree from a graph. And it finds the subset of edges that include every vertex of the graph such that the sum of the weight of the edges can be minimized. And this primes algorithm really take care of only the vertices or the nodes that we have. So it considers the nodes, not the edges. The Crasker considers the edges, but then it's only include the vertices, the primes algorithm. So it starts with a single node and explores all the adjacent nodes with all the connecting edges at every step. And the edges of the minimal weight cause the gap got selected. So this is just a brief description of how it works. So this is how you can actually model the primes algorithm as a pseudocode. So you first have to initialize the MST, which is the minimum spanning tree, with any chosen vertex. Randomly, you can choose any vertex at random. And now we have to find all the edges that connect the tree in the above step. With the new vertices from the edges found, selecting the minimum edge and add it to the tree. So repeat 2 until the spanning tree is formed, and then we are good to go. So I think we have an example here. Yeah, so this is what we have. So we choose an arbitrary value. So we are starting with the node A. And I move on to add the node C. And then moving on, we add the node D here. So it is basically adding the various nodes which has the least edges. And then let me see, we move further to this, then we move to this, then we move to this one as well. And they're getting the same thing as we had earlier on. So the primes algorithm works the same as the Crasker, but then it focuses on selecting vertices. So it includes vertices, but then you consider the weight on the edges. So if you take an arbitrary vertex like A, you look at its neighbors. In the process of looking, you also make sure that you check the vertices. I mean, the vertices and the edges. Which one is less? If maybe A to C is less than A to D, it will choose the vertex C and then move on to the next as well. Please, any question? So as just a simple assignment, this is another one for you. Can we do it before we leave?
Let's try it.
Let's
All right,
try it,
so
sir.
someone should take the lead. I will draw so that you all see the direction. All right, so somebody should take the lead for us.
So we are using the times algorithm, right? So we start from 0. Yes, let's start from 0.
Just a minute, please.
So when we take 0, so
You start from 0.
yes, then we look at from 0 to 1 and 0 to 7, the least one.
Okay.
So we will take 1.
Okay.
Then
so
we look at
direction.
1. Yes. Then from 1 we look at 2 and 7, the smallest one. So we move to the 2, which is 8.
You said 2 and 7.
Yes, note 2 and note 7.
Yeah, but
The
it's 1
least
and 2.
width.
7.
So we take.
Okay, so we take which one?
Yeah. So we will go to the note 7.
Okay.
The note 2. The note 2. Yes. Yes. No. The note 2. We are on the note 2. Then the note 2 from 2 to 3 and 2 to 9. The 2 to 3 and 2 to 8. The 8 is smaller. So we move to 8.
Okay, yeah.
Then we continue to 6.
Continue to 6. 2 to 6. Oh, which one?
Okay, no, yes. Then 8. We move to 6.
Move to 8.
6.
Okay.
Then we move to 7.
Move to 7.
7. Then from 6 to we move to 5.
Okay, move to 5.
So 5. 5 we move to 4, then 3.
We move to
3.
4 and then 3. Do we all agree?
Yes, sir.
Do we all agree? Do we all agree, please?
Sir. Sir.
Hello, I'm something is.
My problem has to do with the 0.6. Now we move to 7 and come back to the 5. Like
7 come back to the 5. Okay. No, but do you agree to what he just said? Is it correct? Like
Looking up to the minimum, I think, I'll second. But the problem has to do that the 6 we move to 7 and we come back to the 5. Like
I'll talk to that, but I also think this is a minimum spanning. I mean, this is a spanning tree, but then I don't think this is a minimum spanning tree. Let's add the weight and put it down, and then later you clean the graph and then try to draw it again and see if you get another smallest minimum sum. So we have 4 here, right? And then we have 8. So 4 plus 8 is 12. And then we have 2 here, which is 14. And then we have 6 here. 14 plus 6 is 20, right? We have 1 here, which is 21. We have 2 here, which is 23. We have 10 here, which is 33. And then we have 9, which is 33 plus 9, 41, 42. Okay. So we are having 42 here. So let's take note of it. Let me clean it again, and then probably someone can help us understand. Get another one. So can anybody help us again? The first spanning tree we drew, we had 42 for the sum of the weights. Do you think we can get a very smaller value less than 42?
Let's start from 7 to let's start from 7 and see. 7.
We start from 7.
Yes.
Okay, let's start. All right, so starting from 7.
Let's start from 7 first. Yes.
So please, are we following or just any other following?
We are
so
following.
We go to 6. We'll go to 6. 6.
Okay.
Then we move to 5.
Move to 5.
Yes. Then we move to 2.
Okay, move to 2.
Then we move to 8.
We move to 8. 8. Yeah, you mean this one here?
No,
8,
from
okay.
2 to 8. From 2 to 8. From 2 to 8. No, 2 to 8. Not from 6 to 8.
Okay.
Then from 2, we go to 3.
2 to 3. 2 to 3. Where is 2 to 3? Okay, here.
Yeah.
Okay.
Then we go to 4.
We go to 4. Where's 4? Okay, no, here 4. Okay.
And then from 2 to we can go to 1 and 0.
So 1 and then 0.
And 0. Yes.
Well, I think this is all right.
Yes, we have visited. Yes, we have visited all the notes.
So if we try to add any of them, we are going to form a circle. All right, so now let's add the weights and see if you have a smaller value compared to this. Right. So I have 4 plus 8, which is 12. 12 plus 2, 14. 14 plus 1, that is 15. 15 plus 1, 17. 17 plus 4, 21. 21 plus 7, 28. 28 plus 9.
30.
That is 37.
37. Yes.
37. So this is quite smaller compared to the 42. Right. So now let's do this together. So let's choose the arbitrary value to be 0 here. Okay, to be 0. Now from 0 to 1 and 0 to 8, the minimum edge is 4. So we go here. And then also we are now notice that every vertex that we visit, we still have in memory the length of the other edges to the other. So we now still have 0 to 7, 8 with 8 in memory. Is it clear? All right, so when we get here, this is from 1 to 2 and from 0 to 7. This value is still in memory. So we have 8, 8, which have the same age. So we can choose to take any of them and it's going to work fine for us. And now as 2, we have 2 to 8, 2 to 7, and then 1 to 7 and 0 to 8. So among all of these, which of the edges is the least? That is 2 to 8, right? So 2 to 8 here. Please, I hope we are following.
Yes, sir.
All right. Now let's move on to the next. And then we have this 8 in memory, we have this 11 in memory, we have this 7 in memory, and we have this 4 in memory, and then this and this in memory. So considering all of these ones I've mentioned, which one is the least? Obviously, this is the least, so we connect this one, forming the non-spanning tree. I hope it's clear. Now we have 2 in memory, 7, 6, 7, 11, 8 in memory. So what do we do next?
We move to the
so now I have to connect from 5 to 6 because that is the link. Now we have 8, 7, 7 in memory, 11 as well. And now we have this one as well from 6 to 7. The value is 1, which is less than all the others that we have explored. We know. Please. And now let's look at this. We have 8, 11, 7, 6, 7 in memory. But which of them is quite smaller? 7 is smaller. So we can connect this and move on. But when we connect this, we are going to get a circle. From 7 to 8, you're going to get a circle. So we'll ignore it and move on to the next smallest, which is 2 to 3. So you connect 2 to 3, and then we are good to go. Now we have memory 9, 14, 10, 11, 8, and 7. Now if we try to connect this 11, which is 1 to 7, we are going to get a circle. The same way, 0 to 7, you're going to get a circle. 7 to 8, you're going to get a circle. So all these trees are disqualified. Now we move to the left. And the only one left is this 3 to 4. So we connect this one over here. Now we have 14 and 10 in memory, but all of these ones, if we connect them, we're going to get a circle. So we don't have to connect. That is the end of our process. So let me try to draw it quite properly for us to see. So this is what we're going to get. So we have from here, we have this, and this one also. Then we have here this and this. So now let's try to add the weights and see if it is less than any of these. Then we can take it as a minimum spanning tree for the 3 spanning tree we've just drawn. So we have 4. Let me change the color. So we have 4 plus 8, which is 12, plus 2, which is 14, plus 1, which is 15, plus 2, which is 17, plus 4, which is 21, plus 7, which is 28, and then plus 9, which is 28 plus 9. Please, what's the answer?
37. 37.
28 plus 9. Yes, 37. So that is.
So your screen is not showing, so you are not getting the figures, please.
37 and 37. So any of the minimum please, can you? I didn't hear what you said earlier.
I think the calculation I was writing, but it seems your screen just get off. So I didn't get the last one.
These are so we have this one here, which is 4. We have this 8, which is 12. We have this one 2, which is 14. We have this one, which is 1, which is 15. We have 2, which is 17. We have 4, which is 21. We have 7, which is 28. And finally, we have 9, which is
your screen is not showing that.
Is it showing now?
Yes, sir.
And please, did you get it?
Yes, sir. Yes, sir. Thank you.
All right. So from the various spanning trees we had from this particular graph, we could see that any of the spanning trees that sum up to 37 happens to be the minimum spanning tree. Right. And what we just did is this one. This is what the minimum spanning tree we just drew earlier on. But maybe at your free time, you can try to explore and see if you get another spanning tree with less weight than 37. Then you confirm for us next week, hopefully. Please, any question? Any question on trees, and then we will close, and hopefully next week we wrap it up. I just heard of only a few boys. I don't know the rest. Are you following? Do you understand what we are doing? Or what is happening?
Oh, we are trying our best to understand.
35. 36 students and others, but I didn't hear a lot of your voices.
So all is not well.
I'm fine.
The background. All is not well.
The next
What is happening?
happens.
Which part is not well?
The next connection is related.
So we are following. Some of us are using devices that does not allow our voice. That's why we are using reaction. So we are following.
Okay. All right, but then if you have the slides, you go through and there are any questions, you can ask next week and then we clarify them before we move on to graphs, and then we conclude with the heaps, and then we'll be done. All right, so without further questions, we'll close here, and then next week we'll continue from graphs. So if you see anything under graphs, just read for a few minutes, and then next week we'll continue from there. All right, thank you so much for joining today, and then see you.
Thank you, sir.
It shall be well.
In fact, it is well. Please, let's meet on the page and continue the discussion.
It's well.
Hello.
The class over.